Thank you for attending my talk on solutions to the Kazantsev-Petyashvili, or KP, 1 and 2 equations via the Zakharov-Manakov stressing method. My name is Patrick Nabelek, and I'm from Oregon State University. And it's a pleasure to have the opportunity to speak in the mini symposium on solitons and other localized structures in physical and mathematical sciences at the Nonlinear Science and Complexity Conference 2024 in Yibin, Sichuan, China. I would like to dedicate my talk to Vladimir Yevgenovich Zakharov, who recently died, and he lived from 1939 to 2023. And I'll discuss some research that came out of various discussions I had with Vladimir. And he was a phenomenal teacher, mathematician, poet, physicist, and poet. And then I would also like to help other people who have helped me along the way on my KP and KDV, and then also like algebraic geometry kind of journey into understanding these various topics. Values of C0, alpha, beta for the shallow water waves with capillary forces. Okay. So here, lowercase x, y, t, and eta are dimensional variables. We want to make them dimensionless. We want to put them into what we call the canonical form, which is a form we get from the book that is just a dimensionless form of the equation, the physical equation. So to get to their dimensional variables, we just make this fairly simple change of variables. And with that, we end up with, in the gravity dominant case, we end up with this expression. And for the capillary dominant, we end up with this expression, where the main difference here is just this plus or minus sign. Now we note that this one is related to a reference from Localized et al. And then this is slightly different than the KP1 though. So our KP2 is the one from the Localized et al. And the KP1 is a slight different version from theirs. Notice that in our rescaling, we've taken time to the negative. So that means actually going backwards in time in our U equation is actually physically going forwards in time. So I'm sorry if this leads to maybe a little bit of confusion. All this means is that time runs backward whenever you see an image. But now when I write equations for U, instead of using the capital variables, I'll just use lowercase variables too. And now here, all the variables are dimensionless because U is the dimensionless variable, where if we use eta, x, y, and t have dimension. So that's, and we note that kind of this KP2 solitons have been studied experimentally and looking at mock reflections of solitons, although we note that they had to go and use that ZCS formulation for the actually to generate the fourfold amplification predicted by KP. So here's just Zakharov's derivation of the KP equation for water waves, and we assume a unit fluid density equal to 1. So this is really nice because we just start out with writing out our Hamiltonian. This is the total energy. So this is our kinetic energy. And then the other terms here are potential energies. One is for the gravitational force, and one is for the surface tension force, or the capillary force on the surface. Well, from this, we can generate our canonical equations of motion, which actually match the usual Euler equations of motion for the water wave system. Now, what Zakharov did from these equations of motion is he just assumed, well, let's just expand the Hamiltonian in a small parameter, or like wave steepness for deep water waves. Well, we expand h in this nonlinear parameter, and then let's just say we get a good enough approximation to our Hamiltonian if we just chop it off at epsilon to the fourth, right? Just set epsilon to the fourth and epsilon to the fifth and everything else equal to 0, and we just left with this kind of first nonlinear approximation from the linear system. Okay. And now from this, if in addition to this, we have these dispersive waves, in addition, they are unidirectional long waves, well, then we get the KdV equation out of this Hamiltonian. And if they were essentially we looked at perturbations, transverse perturbations that aren't too significant compared to the KdV evolution. Well, then we end up with our KP2 equation for gravity waves, or KP1 if this beta is, and what determines if we end up with KP1 or KP2 is the sign of this beta value here. If it's positive, we get KP2, and if it's negative, we get KP. So how do we make our solutions? Well, I'm actually going to discuss some exact analytic solutions just by applying this Zakharov-Manakov dressing method, and then I'll show some extensions of this to some related concepts and some analytical problems. So what's discussed here is originally introduced by Zakharov and Manakov in 1984, and then I discussed a little bit of this topic and just kind of a summary in the 2020 paper I published. But the way this works is we produce solutions from something called a dressing function. There's just this R0 of KW function here. Well, this is actually usually not a function. It's usually what we call a compactly supported Schwartz distribution. So it could be like sums of delta functions, which is actually a very important case, which corresponds to the solitons, and then the lumps and line and lump chains I'll discuss later as well. Okay. Well, from this R0 of KW that determines, in some sense, determines the solution to the KP equation, well, we can characterize this function by kind of what I might call a joint support. So we take essentially the support of R0 of KW as we let W vary. We take the support in K, and then we let K vary and take the support in W. Produce S1 and S2, and then we just combine those two sets. We take their union to determine this S here, and this is essentially the support of our Schwartz distribution. Now we let this chi of X of K and then XYT. So we want to think of this as a function of K that then has XYT as parameters. We'll turn XYT into variables again later. So for the moment, we just fix X, Y, and T and just look as for a function of K. And then later we'll let X, Y, and T vary. But we'll see there. And then we have this function of K. This is a function on C minus S. So on the complex plane minus our kind of joint support there, that S. And then we can actually extend this to all of the Riemann sphere, which is our projective space, complex projective space P1. And on there we look for a chi that's determined by the fact that it must solve this non-local d-bar problem, NDP, with this normalization that on our Riemann sphere at the point at infinity we have the value of 1. So it's a differential integral equation with then just constraint that at infinity we have 1. Now the KP2 and KP1 equations just enter through, well, in two ways. One way they enter is through this phi function here, which appears in our NDP. Okay, so we use a different choice of phi to produce solutions to KP2 and KP1, and the only difference is this I appearing in front of the Y term. Okay. The other thing is, well, it turns out for most choices of the dressing function, what we get out of this will be a complex and singular solution. So we need to apply additional conditions so that we end up with a real and regular wave. Okay? And these are on R0. Well, from this, we take our solution chi to this problem, we expand it in K inverse, and then we look at our correction. So as we go to infinity, our expansion is 1 plus function chi1 of xyt. Now this function chi1 does not depend on K, and it's from this function chi1 that we get u of xyt that solves our KP1 or KP2 equation depending on our choice of phi, and then the constraints we end up with on R0. Here are some solutions computed using this method. So I have essentially one thing that looks like kind of 3 line solitons interacting, and one thing that looks like 2 line solitons. Or in the top one, where we have this Y-shaped soliton, we have some kind of what we call resonance, which I'll discuss in a bit. We can then, using this method, by going over to the Riemann-Hilbert problem and sort of approach, we can generate this model of what I call a KP2 condensate. So it looks kind of like a kind of nonlinear reaction of solitons moving. We can also do KP1 equation, which in addition, so KP1 equations has line solitons. Problem is those line soliton solutions are unstable for KP1. However, it does have KP, what are called lump chain solutions that I'll describe the history of in a bit. And so here's just essentially just interactions of two lump chains, just two cases of two lump chains interacting. Then we can also go to that Riemann-Hilbert problem, non-local Riemann-Hilbert problem, or non-local D-bar problem. They're equivalent to compute interactions between lots of lump chains, and we choose our lump chain kind of parameters so that in the transverse direction, the lump chains are nicely spread out. So they're not, so we have just a bunch of lump chains interacting. And then the final simulation here, I have KP1. I have a bunch of line and lump solitons interacting. And we imagine an initial condition on the left-hand side here. Notice that on the left-hand side, the red is about 6, just a little more than 6, while purple 0, okay? Well, after enough time has evolved, the lump chains escape from this lump line condensate, and we see even individual lumps emerging from our lump line condensate as well as a lump chain. Okay? So I'm going to explain a little more how these work. So as I alluded to before, to produce the multi-soliton solutions, we just take our dressing function supported on it's just a delta function. And some of the delta functions is with this weighting number e to the phi n, and I use phi here because it's acting a lot like a phase would. Okay, we have our KP2 equation. We choose wave numbers in our parameterization, right? So we have these parameters kn and wn. Well, these are determined by capital Kn and capital Ln, where capital Kn and capital Ln we think of as the components of the nonlinear wave vector, or the wave vector for the solitons, for the line solitons. And here we have our soliton dispersion relation. On the other hand, if we go the KP2 route, our Kn and Wn, well, you have to parameterize them slightly differently, and now they have this I ln over 2Kn appearing, where I remember our capital K and capital L, those are our nonlinear wave vectors. And then we have our nonlinear soliton dispersion relation that determines the kind of nonlinear, what we call frequency, and this really is what determines the velocity of the soliton. Now I give a small remark that this parameterization for KP2 has shown to also be a good parameterization for something called the main component of the Hirota variety in this recent paper by Pavello and Mandelstam, and then also similar formulas for KP1 appeared in this recent preprint by Little in 2024. There seems to be a close relation to some other methods by Agostini, Pavello, Mandelstam, and Sternfeld from 2021, and Agostini, Sedlik, and Little from 2021 as well. And then to get to our solution to our equation, well, it turns out that we actually end up with this linear equation for Fm. Then we know that our solution to our NDP must look like this. And we end up with our solution to the KP equation, 1 or 2, by just looking at the x derivative of the sum of Fn that appear as essentially the residues of all the poles in chi. Now we look at KP1 stable lump chain solutions and unstable line solitons. So here's just a variety of pictures. Above left is work of Lester, Gaylor, Zakharov from 2021, which I believe they'll discuss in, Dimitri will discuss in more detail in the next talk. Here is above center, we have a picture of a genus 2, a periodic KP1 lump soliton, just an individual lump soliton, but periodically extended in both X and Y. Then there are some interactions of line and lump chains, line solitons and lump chains by Stepanitz, Zakharov, and Zakharov from 2022. And the cylindrical coordinate version of these pictures were just shown by Stepanitz in his recent talk at the conference here. And then the bottom right, we have recent work by Zhang, Yang, Li, Kyo, Stepanitz from 2023. And again, the cylindrical version was just presented of those of that kind of solutions. Okay, now we have our KP1 lump chain interactions, and here's just two examples. These pieces of the space time of the space and time for the so we're fine. And here's just a statement of that non-local Riemann-Hilbert problem. You can ask questions later. I'll just leave this up for a bit, and then I can show that during the question time if someone has a question. More just, but here's what I produced from the approach. We have our KP2 line soliton condensate. We have our lump soliton condensate. We have our line lump condensate, where we have this emergence of a very large lump in front that's actually connected to a lump chain. Well, this very large lump, we can zoom in on it, and we get very good accuracy as we zoom in on this so we see a fairly complex wave field, but we see some coherent structures within there that are very interesting. The Riemann-Hilbert problem approach, one of the inspirations for that is Schottky uniformization for a periodic and a finite genus solutions to the KP equations as described in the Localized et al. Book from 1994. So here we have our here's their Schottky uniformization U1 for the KP2 equation, and here's the case of a genus 3 curve. And then, well, the thinking behind the jump contours is, well, we could also collapse these circles to contours, and these are then the jump contours for our problem. When we essentially have our one-sided condensate, we end up with solutions that have periodic in various asymptotic regions. So that's the evidence for this approach, really giving us the exact same solutions as we would get from those Schottky uniformization Riemann surfaces described in that book from 1994. Now, in future work, I'd like to kind of extend this to high genus. So for KDV, I worked with Dennis Billman and Tom Trogdon for periodic KDV using the Riemann-Hilbert approach. And we have genus 30 a condensate. This is just 30 genus 30 solution. I call it a condensate because that's essentially the periodic version of 30 solitons interacting. So that's why I call it a condensate here. That's why I use that terminology. So now, does this describe a rogue wave in the ocean? So if we look at this wave actually as an animation of this wave, it looks similar to a breather. So is it some kind of breather-like solution to the KdV equation? Is it something else? I don't know what this is. But I do know it's a solution to the KdV equation that's genus 30. We then took our genus to genus 300 to numerically observe a dispersive quantization in solutions of the KdV equation, which is shown here. See these papers for more information on background on that. Now, it turns out that when you get to infinite genus surfaces, they're not just described by their genus, but they're extra kind of typing to it. So we actually call them infinite type surfaces. And then it turns out the holes can do weird things in infinite genus limits. So one thing they can do is they can just collect at a point. And this is what happens with what's known as a Loch Ness monster, where you just take a Riemann sphere and just keep adding on donuts to it. Okay? To get an infinite number, collecting at a point. On the other hand, that would have one end. On the other hand, there's these things, and in studying your dispersive quantization, to conjecture that we really don't have oscillations in the interior regions of these piecewise continuous curves. So we zoom in near the middle, and we see that as we take the genus up to 900, the artifacts appear to go away. Works described here come from various sources, and a lot of kind of the inspiration for these ideas came from Sofia Kovalevskaya, Andrei Kolmogorov, Klaus Hasselmann, Ludwig Fadyev, and Vladimir Zakharov. And so thank you for attending my talk. And I also just wanted to end by since this is dedicated to Vladimir Zakharov, just end with explaining how kind of his contributions intersected with some very important contributions to just physics and mathematics.